Hello, everyone. Thank you for coming to this session. My name is Jun. I'm a senior data scientist at Lyft, tech lead for the Lyft Rider app science team. And a big part of my work is to use machine learning method to optimize and improve top-line business metrics, such as the conversion rate of Lyft ride requests over the entire US market. So working with machine learning at such a large scale, the productivity of my model training work is really important because it frees up my time to focusing on solving more business problems and deeper business problems. And today I want to introduce distributed hybrid parameter tuning. It's powered by an open source library called Fugue-tune. If you also work with machine learning models and there is a parameter in your model, this talk is for you. A quick intro to Fugue-tune library before we start, as we're going to do a lot of demo using it today. Tune is an abstraction layer of general hyperparameter tuning. It has integrated popular hyperparameter tuning frameworks such as Optuna and HyperOPT. It has also integrated machine learning lifecycle management frameworks such as AlmaFlow and weights and biases. And in addition to that, Tune is built on Fugue, so it can seamlessly run on any backend supported by Fugue, such as Spark, Dask, and Local. And both Tune and Fugue are open sourced. For today's presentation, I'll first give an introduction to the hyperparameter tuning problem in machine learning, and then discuss some common pain points from a data scientist point of view. And then I'll talk about how those pain points are addressed by Fugue-tune. And with real case examples, I'll show you how to construct hybrid search spaces, and also some advanced tricks, such as how to distribute the tuning job on Dask and monitoring the tuning job with weights and biases. And to start, let's recap the problem of hyperparameter tuning in machine learning. Hyperparameter tuning plays a critical role in the machine learning workflow. Almost every machine learning model in the industry today has a hyperparameter that must be set to generalize to the problem and the data set. And if we use suboptimal set of hyperparameters, that will directly result in lower model performance. In particular, it will cause model to underfeed or overfeed to the training set. The essence of parameter tuning is really straightforward and simple. From a given search space on the left, we want to find a set of hyperparameters that can maximize or minimizes the objective function on the right, which can be a function that takes the input of hyperparameter set, run the machine learning model, and evaluate on the validation set. Well, this is a simple process. However, to build such tuning flow could be cumbersome. And I'll give you a concrete example that is common in every model developer's work. And this problem is very simple, yet there's no elegant solution so far. So Han is working on the California housing prediction problem on Kaggle. By the way, Han is the creator of this Fugue-tune library. Han looked over the discussion board and he noticed that many people are using XGBoost and LetGBM. So naturally, Han decided to try both. Usually I and many other data scientists, we try even 7 to 8 modeling methods and then to get the best result. And Han also want to tune roughly tune the parameters to compare between the models. So because XGBoost generally takes longer to train than LetGBM, so Han decides to use research for XGBoost and Bayesian optimization for LetGBM. And I'll pause here for a second and let's think together. If you were Han, how are you going to design this search space and this tuning flow? And I'll think out loud here. So first of all, no matter what tuning framework to use, we need to define an objective function to optimize. And in this problem, I need a function that trains and cross-validates this model and then outputs the metric score to measure the model performance with different modeling methods and different hyperparameter sets. And here we're outputting the average of mean absolute percentage error across the validation sets. And next is the important part to define the search space. Intuitively, I need the search space for XGBoost, where I do grade search on, say, n estimators. And then I need another search space for LetGBM, where I want to do Bayesian optimization. And then I'll use some optimizer to find the best set that gives the best model result in the union of these two spaces. And this is really simple and easy, like logic, right? Now let's code it. So as you can see, even using the simplest existing tuning framework, Optuna, the code would be this long. And this is because first, different tuning methods are exclusive to each other. So users need to define separate objective functions to use more than one method. And second, to do grade search, parameters have to be declared twice and in different ways. But going back to our original problem, all we want to do is this little piece. So we wonder, couldn't there be a simpler and more elegant approach? And next, I'll introduce a Fugue-tune solution. So on the left side, we have the code defining the search space and the optimization flow using Optuna. On the right side is Fugue-tune's code. And note that in Fugue-tune, we're also using Optuna as the local optimizer for Bayesian optimization. So these two code snippets are doing exactly the same thing, but we can see Fugue-tune's code is much shorter and more intuitive. In Fugue-tune, model search, grade search, random search, and Bayesian optimization, they can be combined intuitively into one space using simple space operators. For example, in this example, we use the plus operator to take the union of the two search space for two different algorithms. And also, there is zero redundancy on defining any parameters using any searching method. In the next section, I'll walk you through how to construct any kind of hybrid search space you want using Tune's keyword and space operators. Apart from the manual choice, there are three main searching parameter tuning algorithms. Grade search is the most commonly used tuning method. It exhaustively searches through a set of user-specified parameter choices. And the result is deterministic, so it's good for categorical categorical parameters, such as modeling methods or whatever we want to make sure to traverse through all the options. However, it is extremely inefficient because the computational complexity increases exponentially with the number of parameters. And grade search is defined using the keyword grade in Tune. Random search, on the other hand, gives users the control on the number of total iterations. It can outperform grade search, especially when only a small number of hyperparameters is affecting the final model performance. However, because each guess is independent from the previous one, it normally requires a large number of samples to achieve a good result, which may be limited by the time and resources. And in Tune, random search is defined using the keyword rand and choice with a given number of samples. A third well-adopted tuning method is Bayesian optimization. Different from random sampling, Bayesian optimization builds a probabilistic surrogate model for the hyperparameter itself and iteratively makes the next guess based on the previous observations. It was proven to be able to achieve a better result in fieldwork evaluations. However, its intrinsic sequential process cannot be parallelized. So it may take a longer time to finish. And in tune, Bayesian optimization is defined using the same keyword as random search without specifying the number of samples. All right, here comes the amazing part. We're putting different type of space together. This is only feasible using Tune. Because Tune allows users to define hybrid search space using these simple space operations. For example, here we define a random space for parameter A and a gray search space for parameter B. And we can use the plus sign to take the union of these two spaces. And we also defined a Bayesian optimization space for parameter C. And here we're multiplying this Bayesian optimization space to the union of random and gray search space. And then in the generated search space, you can see we have 4 samples. 2 of them are from gray search of A, choosing from 2 options. A is a random search. Yeah, they're random. 2 of them are from A, is a random search in the range of 1 to 2. And 2 of them are gray search on B on the 2 options and X and Y. And each of them are followed by a Bayesian optimization on parameter C as a second layer of optimization. And it's okay if you haven't fully got the idea. Let's do a demo. So Tune has 2 space operators, plus and the union and cross product. I'll do one example for each and lastly put them together. So the first one is plus operator. It is used for taking the union of 2 search spaces. So this example here is similar to the California housing example, where we want to try 3 modeling methods, and we want to tune their parameters using different tuning methods. So here we are doing gray search for XGBoost, random search for LetGBM, and a Bayesian optimization for CADBoost. And we add these 3 space together to take the union of them. And you can see in the generated search space, we have 2 samples for XGBoost. They are from doing a gray search on 2 options, and 3 samples for LetGBM on a random sampling of 3 samples. And lastly, a Bayesian optimization on CADBoost. And the other operator we can use is the star operator for cross-product space. So for example, now we know that LetGBM works the best for our model, and we want to fine-tune LetGBM. Then in the new search space, we can ping the model on LetGBM regressor. And likely, we can also pin another metric, say an estimators, as it may be limited by, say, online inference computation constraint. And then we may want to do a gray search on the boosting method so that we can make sure we'll definitely try both of them. And next, we may want to do a random search on feature fraction if we think it's not super important to the model performance. I just want to try a few options, but I don't want to allocate too much resources. Then I can do a random search with only 2 samples. On the other hand, we may want to do a fine-tune on the learning rate if we believe it's important to final model performance. So I want to allocate more resource, and I want to do a Bayesian optimization. And recall that for Bayesian optimization, we don't want to specify a sample on the space. Otherwise, it became a random search, so it's a separate Bayesian optimization space. And you can also organize this to be like static space, gray search space, random search space, and Bayesian optimization space. Because putting them together is really easy with this star operator. So here we multiply the non-Bayesian with Bayesian space. And you can see in the generated search space, we have 4 samples. They are coming from 2 gray search multiplied by 2 random search. And each of them are followed by a Bayesian optimization on the learning rate. And lastly, let's see how to use both of the operators to construct any combination of search spaces we want. So for example, here again, we want to try out all three modeling methods. This time we want to tune their common parameter and estimators. So maybe before we need to implement this 3 times for each of the model, but using tune, we can just define 3 model space and just the 1 Bayesian optimization space on the common parameter. And then we take the union of the model space and multiply by the Bayesian space on the common parameter. So you can see in the generative search space, we have 3 samples. They're using different modeling methods, and all of them are doing a Bayesian optimization on the common parameter. All right, so far we have discussed the definition of hybrid search space. And next, let's talk about another really important part, distributed tuning. So model tuning job at the large scale, it can take a single machine forever to run. Well, parallel computing is the solution. However, it will require a significant amount of effort on code change and advanced domain knowledge to do it right. So recall that Tune is built on Fugue, so we can easily distribute the tuning jobs to thousands of machines and run them parallelly. And all we need to do is to specify the execution engine on Tune's suggested method. And here we do not need to write any Spark or Dask code, nor do someone need to know Spark or Dask at all to parallel their model training job effortlessly. And in the next section, I'll show you some other advanced knowledge of Tune to further increase our modeling productivity. And after which, we will put them together in the California housing example. So starting from result monitoring, it is very important to monitor the tuning process at real time and properly log all the results, especially when we're doing parallel computing. And again, this can be achieved easily through just customizing 1 parameters in Tune's suggested method. For example, to automatically track all the model scores and parameters with weights and biases, we just need to set the logger to weights and biases and give it a project name. And there's no code change like in your model training flow or anywhere else. And in addition to its highly abstracted user interface, Tune's autologging is also very well organized. For example, in weights and biases, within each project, Tune logs 1 group per suggested run. So there can be multiple groups in 1 project, which is really great if you are trying to, say, narrowing down your search space on the same problem, or even you're applying different method to optimize the same objective function, and they will be put together in 1 project as different subgroups. And for each group, there will be subruns where we can see more details on how this metric got optimized over time. And last but not least, because Tune has integrated existing hyperparameter tuning libraries such as Optuna and HyperOPT, we can switch between them seamlessly for different Bayesian optimization algorithms, and similarly within just 1 parameter change. All right, so next let's see how do we put them together in the California housing example. Oh, cool, Dask is working now. So for today, we're going to use coiled Dask client as the execution engine to parallel our computation. And just loading in the data set. Okay, cool. So recalling this California housing problem, we want to tune two modeling algorithms at the same time using different methods. So here we're defining the objective function and the search space. And before the tuning, we can quickly check on the baseline scores. So using default parameter, they're both around 0.18. All right. So next, here's a list of things we want to do for the model tuning here. Fundamentally, we want to evaluate the objective function over a search space we define. And we may want to apply a specific Bayesian optimization algorithm. Say we want to do HyperOPT here. And it would be great if we can distribute the job on task to save some time. And finally, we want to track the tuning result with 1dB and maybe do some fancy plots. And I'll pause here for just 3 seconds and let's quickly think how you may define such a tuning flow. And I'll start typing my answer here. So I'll use the suggest method from Fugue-tune. And I'll just go over my task list. So starting from, I want to evaluate my objective function, where I define it here, called objective. And I want to search it through the union of these two spaces. So I'll pass in the space. And recall that we can use this plus operator to take as many space, the union of as many space as we defined and want to search on. And next, I want to apply HyperOPT for Bayesian optimization. So I can say, here, I'll say local optimizer. I want to use HyperOPT. And because it's an iterative tuning, to save some time, let's do a maximum of 5 iterations. And then I want to run the job distributedly on Spark. And all I need to do is say execution engine is, so here we're using the Coil Desk client, so I'll pass in client. You can pass in either Coil client or Desk cluster. And if you use Spark, you can just pass in Spark session. And lastly, I want to track my result with 1dB, so I'll say logger equals 1dB. If you use MLflow, you can just do MLflow. And we want to give a project name, let's say CA housing tuning SciPy. All right. So good, it's running. So in just calling this one function, one single function, we are doing like this much things. And we can take a quick look if the Wi-Fi, okay, yeah. So in the task UI, we can see how this job gets parallelized. And we're using 8 workers. Each one has 2 engines, so 16 engines here. And we can go to, this is my weights and biases account linked, and refreshing it. Cool. So yeah, we can see the first one is the run we just kicked off seconds ago. And this is the project name. And we can see there's a whole list of projects that is corresponding to whatever name we define. And in each project, we can have multiple groups. Let me use another run I did yesterday, which has more runs. Yeah, we can have multiple groups, and the overall result is displayed here. And we can easily see that this group, sorry, let me enlarge this a bit. This group C25, this one is giving the best result. And we can click in here and so this is the one suggest method we call, and we can see these 3 dots here. They are the grid search on XGBoost, and this line is the Bayesian optimization on LightGBM. And we can also click into this sub-12 on LightGBM and see how this metric got minimized, optimized over time by Bayesian optimization. And of course, you have everything to we have all the data associated with the model, so we can do some fancy plot like this parallel coordinates plot. Yeah, so that's how to put like everything together. Here we used Dask, HyperOPT, and 1DB. I have another demo in another talk a week ago. It's on Optuna, Spark, and MLflow. It's on YouTube. If you're interested, please feel free to check out. And we may not have time to go over the last demo. I'll be really quick. So in the last demo, we're trying to apply this everything in the tuning to a forecasting problem and using the GridKite library. And the reason we're doing this with GridKite is because it's a really new library, so it has an entirely new objective function, and it's very flexible with a lot of parameters. For example, like here's a whole list of parameters. I'll just go straight to the code for a quick look. So as we can see, this is the objective function for GridKite. I didn't try to add anything to it. It's just how forecasting model looks. There are like a lot of things we can customize and do in the objective function, but this is totally fine for just using it as the tuning objective in Fugue-tune, because Fugue-tune allows users to define the objective function in native Python language, and they will convert everything to be tune compatible. So which means we don't need to change any of our existing code to use tune, and we just need to pass out the score to evaluate this objective. And similarly, it's really easy to define a search space, even though we have a lot of parameter here. It's very clean and intuitive, and we can apply mixed type of tuning methods. And this, the demo of this is also online. So to summarize today's presentation, we have covered 3 major parts of distributed hybrid hyperparameter tuning: the definition and construction of a hybrid search space, the distributed model evaluation and result monitoring, and lastly, how to apply everything to a general and complex machine learning objective. I hope you are excited to try this out on your own machine learning problem. And both of the libraries we demoed here today are open sourced, and all the notebook and recordings are available online. Please feel free to check them out. Thank you so much. I'm happy to take any questions.
Much for this great talk, Jun. We have some great questions. Logan is asking, when using the hybrid search, do you run a Bayesian optimization for a parameter independent of another parameter's grid search?
Can you repeat the last sentence?
Sure. Do you run a Bayesian optimization for a parameter independent of another parameter's grid search?
Oh, yeah. So it's let me quickly go back to the hybrid search space slide. So first of all, we define one search method to one, each parameter has, well, we assign one search method to each variable, and the Bayesian optimization is on the top layer of grid search and random search. You can think like random search and grid search, they are first being defined, like the number are pinned there, and then we're doing a Bayesian optimization on top of that.
Carl is asking, is it any harder to run nested cross-validation with Fugue-tune versus pure scikit-learn hyperparameter optimization?
Oh, you can use any modeling method. Fugue-tune is model agnostic, platform agnostic. It can be also a general hyperparameter tuning library, not necessarily for machine learning problems. So the objective can be anything, as long as there's an output score to evaluate the objective.